Hello everyone. So in this pre-lecture tutorial, we're going to discuss how we approach quantitative problems involving weak acids. If you recall in the last pre-lecture tutorial, we dealt with strong acids or strong bases. And there, the procedure was made quite a bit simpler with the idea that, again, since we have a strong acid or a strong base, dissociation proceeds 100%. And so the initial concentration of the acid or the base ended up being the initial concentration of the hydrogen ion if we were dealing with a strong acid, or through the stoichiometry of the base dissociation process, then we could figure out what the initial concentration of the hydroxide ion was, again assuming 100% dissociation. However, as we're aware, when we're dealing with a weak acid or a weak base, but in this particular tutorial we'll focus on weak acids, dissociation does not proceed 100%. And so we have to find a way to deal with that complication mathematically. And so there's an example problem here on the slide. Before we get into it, I just sort of want to preface the theory a little bit. In this particular problem, we're dealing with formic acid, which is a weak acid. Now, as a weak acid, basically the dissociation to hydrogen ion and the formate ion does not occur 100%. It's an equilibrium process. Basically, it occurs to a certain extent in the forward direction and to a certain extent in the backward direction. And as with any equilibrium process, there is an equilibrium constant that can be written for this process using the law of mass action. So again, assuming we have an aqueous solution of formic acid, and the dissociation occurs partially to give us some hydrogen ion in aqueous solution and some formate ion in aqueous solution, this equilibrium constant can be written as such: the hydrogen ion concentration times the formate ion concentration divided by the concentration of the formic acid, again, all at equilibrium. Now, again, in this particular case, the formic acid is donating a proton. Basically, a proton is falling off the structure of the formic acid, and so as a result, the formic acid is behaving as an acid, and this particular equation represents an acid dissociation, and so this equilibrium constant we can call Ka, an acid dissociation constant. And so we can use some of the strategies that we learned in chapter 15 to go ahead and solve these types of problems. And so now let's go ahead and take a look at the rest of the problem. We're told that we have a 0.1 molar solution of formic acid and its pH is 2.38. And from this information alone, we're to calculate the value of Ka. And so the important thing to keep in mind is that when we have a pH measurement like this, basically this reflects the pH at equilibrium. And since pH is equal to the negative log of the hydrogen ion concentration, this pH measurement will allow me to find out the equilibrium concentration of the hydrogen ion. So I can find that concentration by taking 10 and raising it to the negative pH power, or in this case 10 to the negative 2.38 power. If I go ahead and run that calculation, then I get an equilibrium concentration of hydrogen ion of 4.2 times 10 to the negative third molar. And returning back to my equation that represents my acid dissociation, which is an equilibrium process, just like in the last chapter, I can construct an ice table. And initially, my concentration of the formic acid is 0.1 molar, and in the instant in which the formic acid is placed in solution, there is no hydrogen ion or formate ion just yet. But I know that at equilibrium, I have a hydrogen ion concentration of 4.2 times 10 to the negative third molar. So that means that my change for the hydrogen ion concentration had to have been plus 4.2 times 10 to the negative third. And since the stoichiometry of the reaction is 1-to-1 across the board, then that means that the change for the formate ion also had to have been plus 4.2 times 10 to the negative third. The change for the formic acid, however, is negative 4.2 times 10 to the negative third. And so I'm going to go ahead and add vertically for my remaining two columns in my ice table, and that means my equilibrium concentration of my formate ion is also 4.2 times 10 to the negative third molar. And if I subtract 4.2 times 10 to the negative third from 0.1 molar, I get 9.58 times 10 to the negative 2 molar in my formic acid concentration at equilibrium. Now that I have all of my equilibrium concentrations, now I can go ahead and plug in to my expression for Ka, and I should be able to come up with a quantitative value. So that should be 4.2 times 10 to the negative third times 4.2 times 10 to the negative third divided by 9.58 times 10 to the negative 2. And if I go ahead and do that math, then I get an acid dissociation constant of 1.8 times 10 to the negative 4. Okay. Now, another type of problem that we might run across for weak acids is if we're actually given a Ka in advance and we're asked to calculate what the pH of a weak acid solution should be. And so that's precisely the type of problem that is on the screen right now. So let's go ahead and walk through how we would do this. I'm told that I have a solution of acetic acid with a concentration of 0.75 molar. I'd like to find the pH, but I'm given the Ka this time, which is 1.8 times 10 to the negative fifth. So a good first step would be to go ahead and write out my equation that shows the partial dissociation of the acetic acid. So that would be H, C2H3O2, my acetic acid, again an aqueous solution, and it's going to dissociate partially to give me an aqueous solution of hydrogen ions as well as an aqueous solution of acetate ions. And again, I can write a Ka expression using the law of mass action. That would be the hydrogen ion concentration times the acetate concentration, divide that through by the concentration of the acetic acid, where again each of these concentrations in the equation would be an equilibrium concentration. And so once again, this is a problem that can be solved using an ice table, as we learned from the last chapter. My initial concentration of acid was 0.75 molar, and again, in the precise moment when this particular concentration of acid is placed in solution, there are initially no hydrogen ions or acetate ions. The change at this point is unknown. I know that I'm going to gain some hydrogen ion and some acetate ion by Le Chatelier's principle, since the concentration of these species are 0. And so that means that my equilibrium concentration of each of the ions on the product side would be X, and I'm going to lose that same amount in my acetic acid. And so that equilibrium concentration expression for my acetic acid concentration would be 0.75 minus X. So plugging that into my expression for Ka, that would be X times X over 0.75 minus X, and that should equal 1.8 times 10 to the negative fifth. Cleaning this up a little bit mathematically, that's just X squared over 0.75 minus X, which is equal to 1.8 times 10 to the negative 5. And so, once again, noticing how small Ka is, it would be reasonable to make the assumption that X is very small. So small, in fact, that it should be negligible in this difference term on the left-hand side. So that would be X squared over 0.75 is equal to 1.8 times 10 to the negative fifth. So if I go ahead and multiply both sides by 0.75, I get x squared is equal to 1.35 times 10 to the negative fifth. To get x, I would need to take the square root of that same number, so the square root of 1.35 times 10 to the negative fifth. And if I go ahead and calculate that out, that would be 3.7 times 10 to the negative third molar. Now, again, we still have to check the validity of this assumption. And so, if you recall, the way we do that is we calculate the percent ionization. I'm going to take this value of x, 3.7 times 10 to the negative third molar, and I'm going to divide by the initial concentration of the acetic acid. That will tell me how much of the acetic acid actually ionized. And if I multiply by 100, it'll do so in percentage terms. If I go ahead and do this math, I get 0.49%. And again, remember that basically our target here is we want to get less than 5% ionization in order for this assumption to be considered valid. 0.49% certainly is less than 5%, and so luckily for us, our assumption was valid. And we could consider this x value to actually be our concentration of our hydrogen ion. So that means that if I just want to calculate the pH, all I need is the negative log of the hydrogen ion concentration. So for us, that would be the negative log of 3.7 times 10 to the negative third. If I go ahead and do that math, then I get 2.43 as my pH of this 0.75 molar solution of acetic acid. Okay, so go ahead and try the follow-up assignment. You're given a selection of problems that, again, will employ all of these strategies that we've discussed. Again, if you have any questions, by all means, email me, and we will discuss it in class. We'll continue with our application activities and our reinforcement activities, and I will see you guys in class then. Have a good night.